Hey kids, welcome to section 5.4, other types of distributions. Today we're going to learn how to find probabilities for outcomes of variables using four new different distributions: Poisson, hypergeometric, geometric, and multinomial. So first, multinomial distributions. Recall that for an experiment to be binomial, two outcomes are required for each trial. But if each trial in an experiment has more than two outcomes, a distribution is called the multinomial distribution must be used. So, for example, if a survey requires the responses of approve, disapprove, or no opinion, or a person may have a choice of one of five activities for Friday night, such as a movie, dinner, baseball game, play, or party. The multinomial distribution is going to be used in these situations. So, multinomial experiment, there must be a fixed number of trials. Each trial has a specific but not necessarily the same number of outcomes. The trials are independent, and the probability of a particular outcome remains the same. So basically, the only difference between a multinomial and a binomial distribution is the fact that there are more than two outcomes. Now, the formula for finding the multinomial distribution does not have a shortcut. And so basically, you're going to take the n, which is the number of trials, put that on the top. And then on the bottom, you're going to divide by how many different outcomes there are going to be, multiplied by the different probabilities with the number of times it's occurring. And then you multiply all this lovely stuff up. And then you round to 3 decimal places. So this formula looks really crazy, but kids, it's not that bad at all. So here's an example of a multinomial distribution. In a large city, 50% of the people choose a movie, 30% choose dinner and a play, and 20% choose shopping as a leisure activity. If a sample of 5 people is randomly selected, find the probability that 3 are planning to go to a movie, 1 to a play, and 1 to a shopping mall. Okay, so we have 5 trials altogether. However, we have 3 different outcomes. Notice that 50%, 30%, and 20% total 100%. So I have 3 outcomes here and 3 corresponding probabilities. So I have my first X occurring 3 times going to a movie, and the probability of going to that movie is 50%. My second outcome is that one person is going to a play, and the probability of going to a play is 0.30. My third outcome is that one person will go shopping, and the corresponding probability is 0.20. So when I go over here to figure out what my probability is, I'm going to do n factorial on top, which is 5 factorial. And then on the bottom, we're going to put the different outcomes that we want with factorials. So 3 factorial, 1 factorial, and 1 factorial. Then we're going to multiply by the first probability, 0.50, to the first x value, 3, times the second probability, 0.30, to the second x value power, 1, times the third probability, 0.20, to the third x value power, 1. If I type all of this into my calculator, I get 0.150. So basically a 15% chance that if I sample 5 people with these 3 possible outcomes, I will get 3 going to a movie, 1 to a play, and 1 to the shopping mall. It's crazy, 15%. All right, let's do another one. A small airport coffee shop manager found that the probabilities that a customer buys 0, 1, 2, or 3 cups of coffee are 0.3, 0.5, 0.15, and 0.05 respectively. If 8 customers enter the shop, find the probability that 2 will purchase something other than coffee, 4 will purchase 1 cup of coffee, 1 will purchase 2 cups of coffee, and 1 will purchase 3 cups of coffee. Well, because the other thing we can do is we can keep track of all of these by doing like the well, we could just yeah, never mind. All right, so we have 8 customers altogether. My first outcome 0 x sub 1 is equal to 0. So my first outcome, why did that just look horrible? So my first outcome is that I can have 0, and that happens 2 out of the 8. So 2 out of the 8 is point 0.4. Wait, what? Oh, 0.3 right there, 0.3. Then we have our second x value, our second outcome is going to be 1, and the probability that it's 1 is going to be 0.5. Our third outcome is that it can be 2, and the probability for that third outcome is 0.15. The fourth outcome is 3 cups of coffee, and the corresponding probability is 0.05. So when I go over to calculate my probability, I'm going to put 8 factorial in the numerator. In the denominator, I'm going to have my different outcomes. Wait, hold on one second. These outcomes are not supposed to be what the actual outcomes are, but they are supposed to be the number of people that do that. So this x should be x sub 1 should be 2 because 2 people are going to purchase something other than coffee. There we go. The second x value is 4 because 4 people will be purchasing 1 cup of coffee with a 50%. Yes. Okay. So then we have 1 and 1. Sorry for the confusion. That was crazy. All right. So on the bottom are the number of people that are doing something. So 2 factorial, 4 factorial, 1 factorial, and 1 factorial. So I'm going to say I totally meant to do what I just did on purpose because the values in the denominator should add up to the value in the numerator. So 2 plus 4 plus 1 plus 1 is 8. And 3 plus 1 plus 1 is 5 in the previous problem. So that's how I knew that something was wrong. So that was a good check that we did. Now we're going to multiply by the first probability 0.3 to the first exponent 2 times the second probability 0.5 to the fourth power times 0.15 to the first power times 0.05 to the first power. All right, that looks super fun. We type all this into our calculator, we get 0.035. So basically there's a 4% chance, which is super small, that if I ask 8 customers what they are going to purchase, that they will purchase. 2 will purchase none, 4 will purchase 1, 1 will purchase 2, and 1 will purchase 3. Crazy. Very small probability. All right, let's get some colored balls. A box contains 4 white balls, 3 red balls, and 3 blue balls. A ball is selected at random and its color is written down. It is replaced each time. That's key because that means the trials are independent. Find the probability that if 5 balls are selected, 2 are white, 2 are red, and 1 is blue. Okay, so I've got n equals total balls that we are pulling is 5. Our first outcome that we want 2 to be white, and the probability that the balls are white is 4 out of 7, 8, 9, 10, 4 tenths, which is 0.4. The second outcome that we want are 2 red balls, and the probability of a red ball is 3 tenths or 0.3. The third outcome that we want is 1 blue ball, and the probability of a blue ball is 3 tenths or 0.3. So to find the probability, I put n factorial or 5 factorial on the top. Then on the bottom, we have our x values with factorials. So 2 factorial, 2 factorial, and 1 factorial. Remember, the bottom numbers 2 plus 2 plus 1 should equal the top 5. Now we're going to multiply by 0.4 to the second power times 0.3 to the second power times 0.3 to the first power. Type all this into our calculator, hit enter, and you get 0.130. So a 13% chance that if we grab 5 balls, 2 are white, 2 are red, and 1 is blue. So that's a multinomial distribution. Next, we're going to move on to the Poisson distribution. Poisson. So a discrete probability distribution that is useful when n is large and p is small, and when the independent variables occur over a period of time is called the Poisson distribution. In addition to being used for the stated conditions, the Poisson distribution can be used when a density of items is distributed over a given area or volume, such as the number of plants growing per acre or the number of defects in a given length of videotape. So you're looking in a certain interval for the probability of something happening. So 4 requirements for the Poisson experiment. Number 1, the random variable x is the number of occurrences of an event over some interval. So I'm giving you some length of videotape. So these 10 minutes, or these 3 feet, or this many cubic centimeters. Number 2, the occurrences must be random. Number 3, they must be independent of one another. And number 4, the average number of occurrences over an interval is known. So I have to already know how many defects are going to be in this 10-foot piece of ribbon already on average before I can find the probability of finding that many. The rounding rule is 3 decimals, just like the previous problems we did with probability. The formulas for the Poisson distribution are in this blue box here. So we have the probability of x occurrences in an interval of time, volume, area, etc. for a variable where lambda, it looks like a little house or a witch's hat. The Greek letter lambda is the mean number of occurrences per unit. So I have 6 defects per foot, or 7 sidewalk marks per 10 meters. I don't know. Notice that the formula for the probability is going to be e to the negative lambda times lambda to the x power, all divided by x factorial. Notice this letter E that's in here. There is a E button on your calculator that I will show you in a minute. It is the same E that you've used in logarithmic and natural logarithmic equations. It is equal approximately to 2.71. So if you ever hear someone talking about the mathematical letter E, kind of like the mathematical letter pi, it is a variable and it's approximately 2.71. So let's see how we deal with the Poisson distributions. So if there are 200 typographical errors randomly distributed in a 500-page manuscript, find the probability that a given page contains exactly 3 errors. All right, so I have a 500-page book, and I know that within that 500-page book, there are 200 errors. I want to know if I randomly open that book up to a page that I will find exactly 3 errors. Okay, well, we can use the formula. The formula needs, if you look back, a lambda and an x. Lambda is the number of occurrences, and x is the probability that we're finding. So for lambda, I know that there are 200 errors in a 500-page manuscript. So my occurrences are 200 out of 500 pages. So that gives me a lambda value of 0.4. So basically, there's roughly 0.4 errors per page, is what it's saying. Our x value that we're trying to find is 3, exactly 3. So I'm going to find the probability of getting exactly 3 as doing e to the negative lambda, or negative 0.4, times lambda, which is 0.4, to the x power 3 over x factorial, or 3 factorial. So let's see how we can type this into our calculators. All right, so let's clear what's in here. Let's get to a fraction. On the top of the fraction, we're going to put e. E is found right here above the division symbol. You have to click the blue second button, and then you can click the division symbol to get an e. Then we need to bring it to the negative 0.4 power. Then I need to multiply it by 0.4 to the third power. Then I can go to the numerator and do 3 factorial. And then hit enter. 3 decimals says 0.007. Now guess what, kids? There is a calculator button that we can use. So if I go back to the calculator and I go to second vars and I scroll up from the bottom, oh, Poisson PDF. So if I want to find the probability of x equals 3, since it is an exact number, I can use the Poisson PDF. Now let's figure out what order stuff goes in the parentheses. So if I click on the Poisson PDF, it needs a lambda and then an x. So my lambda, remember, was 0.4. That's the incidence. And my x value is 3. Then I hit enter a few times, and I get 0.007. So it needed the lambda value and then the x value. So that's going to give us 0.007. So I don't know if you need to write yourself a little note here that it's Poisson PDF and it's lambda and then x. All right, let's do another example. If approximately 2% of the people in a room of 200 people are left-handed, find the probability that exactly 5 people there are left-handed. Okay, so my x and my lambda. My lambda is my incidence. So if 2% of those 200 people are left-handed, that means 4 people are left-handed. So we have 4 left-handers. My x value, I'm looking for exactly 5. So my x is 5. So I can find the probability that x equals 5 by doing e to the negative 4 times 4 to the 5th power over 5 factorial. If I type this into my calculator, I get 0.156. So basically you have a 16% chance that if 4 people are left-handed in this room, well, if on average 2% are left-handed, then in this room of 200, I have a 16% chance that exactly 5 are. Again, small probability because it's an exact number. Okay, let's take a look at this one. A sales firm receives on average 3 calls per hour on its toll-free number. For any given hour, find the probability that it will receive the following. So this average of 3 calls per hour, kids, is our lambda of 3. It already has calls per hour, so I'm good. This one says at most 3. So that means I'm trying to find the probability that x is greater than or equal to 3. So that means I'm doing 3, and then I'm doing 4, and I'm doing 5, and I don't know how many I'm going to stop with. So I'm going to use the Poisson CDF to calculate everything below. So instead of doing x is greater than or equal to 3, I'm going to do 1 minus the probability that x is less than or equal to 2. So this is going to be 1 minus the Poisson CDF of 3 for lambda and 2 for x. So when I do this, I get 1 minus, well, let's go over to our calculator. Let's go to Poisson CDF. And my lambda is 3, and I'm looking for 2. Hit enter. I have 0.423. Let's subtract that from 1. So I can do 1 minus 0.423, and I get 0.577. Oh my goodness, at most 3. Why did I do greater than or equal to? At most 3 is less than or equal to 3. Oh my gosh, I am so sorry. Okay, we're going to scoot that back. Okay, we're just going to start this slide over again. All right, so a sales firm receives on average 3 calls per hour on its toll-free number. For any given hour, find the probability that it will receive the following. 3 calls per hour, kids, that is your lambda. That is your rate of occurrence. So your lambda here is 3. At most 3 calls would be the probability that x is less than or equal to 3. So this means that my x values are going to be 0, 1, 2, and 3. Well, I can either add up those 4 probabilities, or if you remember, so I can do that using by using Poisson PDFs. But if I want to do the shorter way, I can just do the Poisson CDF and use lambda of 3 and my x value of 3. So if I go to my calculator and I go to second vars and I go to Poisson CDF and I do lambda of 3 and an x value of 3 and hit enter, I should get 0.647. So that means that if I'm averaging 3 calls per hour, that during a given hour, there's a 65% chance that I'll have at most 3 calls. Okay, or at most 3 calls. Letter B, at least 3 calls. Well, at least 3 calls means greater than or equal to 3. My lambda is still 3, but my x values now are going to be 3 and 4 and 5 and so on. I don't know where it's going to stop. So here we need to definitely do 1 minus the probability that x is less than or equal to, well, if it's not 3 and higher, it's 2 and lower. So I can do 1 minus the probability that x is less than or equal to 2. So this is 1 minus the, why do I keep saying binomial? The Poisson CDF of lambda of 3 and x of 2. So if we go to our calculator, we can do 1 minus the binomial, Poisson CDF. Lambda is 3, x value is 2. Hit enter. You get 0.577. Okay, finally, 5 or more calls. So I want the probability that x is greater than or equal to 5. So my lambda is still 3. My x's are now 5, 6, 7, and so on. Well, I can't really do that, but I can do 1 minus the probability that x is less than or equal to 4. So that's 1 minus the Poisson CDF, a lambda of 3 and an x value of 4. If I type this into my calculator, let's see what happens. So I'm going to do 1 minus the Poisson CDF of lambda of 3 and an x value of 4. And you get 0.185. Okay, that's the second one. Here comes the third one. Hypergeometric distribution. Hypergeometric. When sampling is done without replacement, the binomial distribution does not give exact probabilities since the trials are not independent. Remember, if you're taking a card out of a deck of cards and not putting the card back in, then you are creating dependent probabilities. The results of the problem can be generalized by using a special probability distribution called the hypergeometric distribution. The hypergeometric distribution is a distribution of a variable that has two outcomes when sampling is done without replacement. So the three requirements to be a hypergeometric experiment must have a fixed number of trials. There must be two outcomes, but now we are using without replacement. The formula for the hypergeometric distribution is down here. This is not a formula that you can do shortcut. The rounding rule is 3 decimals. So basically, what you're going to be doing is you're going to have a choosing situation with combinations that we had from chapter 4. And so we're going to have a certain number of items where we're choosing some of them, and then a certain number of items, and we're choosing out of those. And then we have a total on the bottom. So we've kind of already done something like this, but now we're putting a fancy name, hypergeometric distribution, to it. All right, so 10 people apply for a job as assistant manager of a restaurant. 5 have completed college and 5 have not. If the manager selects 3 applicants at random, find the probability that all 3 are college graduates. Okay, well, in the formula, we have all of these A's and B's and N's and X's. So we have A, B, N, and X. In the problem, the number of trials is going to be 3. 3 applicants are chosen at random. That's your N. The X is the probability that you're trying to find. So all 3 of them are college graduates. So X is 3. Your A value is you get to choose which group you're picking things from. So I'm going to call A my 5 that have completed college, and therefore my B is going to be the 5 that have not completed college. All right, so we're finding the probability that all 3 are college graduates. So out of the 5 that completed college, we're going to choose 3 of them. And then out of the 5 that have not completed college, we're going to choose 0 of them. We are choosing from 10 total people, we are choosing 3. So kids, we've seen this before. We have 10 applicants and we're choosing 3. These 3, I'm going to take 3 college graduates out of the 5 college graduates and no non-college graduates out of the 5 non-college graduates. So we've kind of done this already. This is 5C3 is 10 and 5C0 is 1. 10C3 is 120. So this is 10 over 120, 0.083, 3 decimals. All right, next example. A recent study found that 2 out of every 10 houses in a neighborhood have no insurance. If 5 houses are selected from 10 houses, Find the probability that exactly one will be uninsured. Okay, well, we've got A, B, N, and X. Your N is the number of trials. So we are selecting 5 houses. So that's our N. We are hoping to get exactly one that will be uninsured. That's going to be our X value. Our A is going to be our A is going to be the ones that have no insurance, because our X value is about uninsured. So our A value should be about uninsured. So our A value is going to be 2. And our B value is going to be 8. So if 2 houses are no insurance, then 8 houses are. So I'll put this over here. So 2 houses, no insurance. 8 houses, yes insurance. And so that's how we came up with the A and the B. So now we're going to use the formula probability that exactly one. So remember, we are picking from 10 houses, we are choosing 5. I want, out of the 2 uninsured houses, I want 1 to be uninsured. And out of the 8 insured houses, I want 4 to be insured. Remember from the previous chapter that the 2 bottom left numbers, 2 and 8, should add up to the bottom left number 10. And the 2 bottom right numbers, 1 and 4, should add up to the bottom right number 5. So 2 choose 1 is 2 8 choose 4 is 70, 10 choose 5 is 252. So this gives us 140 over 252, 3 decimals, 0.556. So basically, if I select 5 houses from 10, knowing that 2 out of every 10 houses have no insurance, I have a 56% chance that I pick exactly one that is uninsured. All right, let's see one more of these hypergeometric distributions. A lot of 12 compressor tanks is checked to see whether there are any defective tanks. 3 tanks are checked for leaks. If 1 or more of the 3 is defective, the lot is rejected. Find the probability that the lot will be rejected if there are actually 3 defective tanks in the lot. Okay, so I need my A, my B, my N, and my X. So my N, kids, is the number of trials. Well, we are picking 3 tanks. So that is my N, 3 tanks. For this, I want exactly 3 to be defective. But when I pick these, I can either have, it says if 1 or more of the 3 is defective, it's rejected. Well, that means I can have 1, I can have 2, and I can have 3. So my A value is going to go with defective. And it says that there are 3 that are defective. That's our A value. So if 3 of them are defective and there's 12 altogether, then 9 are not going to be defective or are fine. So now I want to find the probability of 1 plus the probability of 2 plus the probability of 3. Because rejection happens when it's 1 or more. So the probability of 1 means that out of the 12, I'm choosing 3. And if I want 1 defective, that means out of the 3 defectives, I'm choosing 1. And then out of the 9 non-defective, I'm choosing 2. Plus, for the probability of 2 defective, I'm still taking 12 and choosing 3. This time, out of the 3 defective, I want to choose 2. And out of the 9 non-defective, I want to choose 1. Plus, and now the probability of exactly 3, I'm still have 12, choose 3. Now, out of my 3 defectives, I'm choosing 3. And out of my 9 non-defectives, I'm choosing 0. Type this into our calculator. 3 decimals, 0.491 plus 0.123 plus 0.005. Add these 3 up, grand total of 0.619. So basically, there's a 62% chance that the lot will be rejected. Okay, final one, geometric distribution. Another useful distribution is called the geometric distribution. This distribution can be used when we have an experiment that has 2 outcomes and is repeated until a successful outcome is obtained. So flipping a coin until you get a head, or rolling a die until you get a 6. Doing something until you get a certain outcome is what a geometric experiment is all about. So, 4 requirements. Each trial has 2 outcomes that can either be a success or a failure. The outcomes are independent of each other. The third one, the probability of a success is the same for each trial. And number 4, the experiment continues until a success is obtained. Here is your formula for the geometric distribution. The probability of a success on each trial, we have P, probability of success, times the quantity 1 minus P, or 1 minus the probability of success or failure, raised to the n minus 1, and n stands for the number of trials. You guessed it, we're rounding to 3 decimal places still. So let's take a look at 2 examples. A coin is tossed. Find the probability of getting the first head on the third toss. So in the formula, all I need are P's and N's. N is the number of trials, or in this case, it's not the number of trials, but it's the number of trials until you get a success. That means the third toss, so N is 3. The probability of getting a head is consistently 1/2 or 0.5. So my formula says P of 3 for getting it on the third toss is P, which is 0.5, times 1 minus P to the N, which is 3 minus 1 power. So I type this all into my calculator, I get 0.125. So basically, if I toss a coin, there's a 13% chance that my first head will appear on the third toss. Now, guess what? There is a shortcut. It's called the geometric probability distribution. So if I go to the calculator, kids, wake it up. Go to second VARS, geometric PDF and geomet CDF are both there. So this one is going to be on the third toss. So that's a PDF. So geomet PDF. So I can use the probability that x equals 3 as the geomet PDF. Now let's see what goes in the parentheses. I need the p-value and then the x. So my p-value is 0.5 and my x value is 3 for the third toss. If I do this, I'm going to put my p-value first, 0.5, and my x value second, 3. And the answer was 0.125. Look at that, same thing. So when you're doing the geomet PDF, in the parentheses goes your P and then your X. So I guess this is not an N for number of trials. That doesn't make sense. It's X. P and X. But it's really an X in the problem because I don't know the number of trials. It's going to be the third. Yes, okay. So I guess this is an N. There we go. So this is the only one that's not alphabetical. All right, last question, kids. In the United States, approximately 42% of the people have type A blood. If 4 people are selected at random, find the probability that the 4th person is the first one selected with type A blood. So 42% of the people in the world have type A blood. I want to know, if I pick 4 people at random, what's the probability that the first type A blood person is on the 4th pick? So in this situation, my P and my N, my P is the probability of a success. That's type A blood. That's 0.42. And I want this to happen with the 4th person. So my N is 4. So I've got the probability that my X value equals 4, or I guess it's not X, I guess it would be N, but it's a random variable. That's fine. So, well, no, I guess it would have to be an N. Oh, my bad. Oh, let's close that. Oh, I want the eraser. This should be an N, and this should be an N. Okay, here we go. N equals N. All right, so the formula says I take my p-value, which is 0.42. I multiply by 1 minus my p-value, and I raise it to the N, which is 4 minus 1 power. If I do this, my probability is 0.082. Or I can use the probability that N equals 4 by using the GeoMet PDF because it's an exact particular value. I have 0.42 as my probability of a success, and I'm looking for the 4th person. If I type this on my calculator, I do indeed get 0.082. All right, kids, that's the end of section 5.4. If you have any questions, please let me know. And as always, keep calm and keep trucking.